Okay, everyone, welcome to the GOCC. Today we have Daniel McGinnis presenting on piercing families of convex sets that avoid a subfamily with lines. I already talked to you about the community statement, so Daniel, take it away.
Alrighty, Mark. Thanks a lot for inviting me. I'm pretty excited to talk to this. I think this is my first time at a GOCC conference meeting, so yeah, excited to talk here. All right. So so this talk is not so much about combinatorics, but it is into the discrete math like umbrella. So this is more like discrete geometry. So first, before I talk about the specific problem that I'll be going over, I want to first introduce an old theorem where the problem that I'm talking about sort of like stemmed from. So this theorem is called Heli's theorem. It says that if you have a family, which I denote here as F, of compact convex sets in Rd, such that every d+1 sets in F have a common point. So in other words, every d+1 sets have a non-empty intersection, then F can be pierced. So the whole family F can be pierced by one point. And what I mean by pierced with one point is I mean there is one point in Rd that is contained in all the sets of your family. So it's just a fancy way of saying that the sets in the family have a non-empty intersection. So the big theme with Heli's theorem is that we have this local condition assumption on the sets, which is every d+1 sets in F have a common point. So this is local because you're only looking at d+1 sets at one time. And then we derive this global condition, which is that all the sets in the family can be pierced by one point. Okay, so here's an example of Heli's theorem in R2. So I have these three disks, and in Heli's theorem in R2, we want every three sets to have a common point. Now, if my family has a fourth set that still satisfies that every three sets have a common point, then that means this fourth set has to intersect the pairwise intersections of all these three sets. And what Heli's theorem says is that then this fourth convex set has to intersect the triple-wise intersection of those original three sets. Okay. So like I said, there's a bunch of like offshoots of this theorem. One way that we can kind of build from Heli's theorem is instead of like hitting our sets with points, what if we want to like hit our sets with lines? So we want to find lines that intersect the sets in our family rather than points. So here's a definition that'll be useful for this. So a family of sets in Rd is said to have a line transversal if there is a line that intersects every set in the family. So basically it's just a line that hits every set. And here is a local property that we'll be working with. So if we have a family of sets F and R2, so for the rest of the talk, everything's going to be in R2. And if I ever say the plane, that also means R2. So if a family of sets in R2, family of sets in R2 has the TK property, if every K sets in F have a line transversal. So this is going to be the local property that we're working with. Every K sets in our family has a line that hits all of those K sets. So for example, if these family of if these squares are a family of convex sets in the plane, then this family has the T3 property. because as you can see here, every 3 of these squares has a line transversal. All right. Now, another definition that's whose purpose is to capture the global property that we want to derive. A family of sets in F and R2 is said to be Ln if there are n lines for which every set in F intersects one of these lines. So it's just a collection of n lines in the plane, and whenever you look at a set in your family, this set will intersect one of those lines. Okay, so if we wanted to come up with a theorem similar to Heli's theorem in the plane for lines, it would look something like this. If we have a family of sets with the T3 property, does that imply that it has a line transversal? So, yeah.
I think I have an answer to this question.
Yes.
Oh wait, T3 property, never mind. I don't have an answer to this question. I was going to say Heli's theorem says yes, but no, T3 is weaker than common
Oh, yeah.
intersection.
Yes. Yeah, so we could ask, okay, if a family of sets in R2 has a T3 property, does this imply that there is one line that intersects all the sets in our family? That would be like similar to Heli's theorem, and that Heli's theorem said if all 3 sets, or if every 3 sets have a non-empty intersection, then all the sets in your family have a non-empty intersection. Okay, so but this is easily seen to not be true by this example. So yeah, so this family had the T3 property, but there is no line intersecting all 4 of these sets. Okay, but so the T3 property does not imply that you're L1, but does the T3 property imply that you're Ln for some n? If so, what is the smallest possible n? Also, what if you have the TK property? Does this imply that you're Ln for some n? And if so, how does this n change as a function of k? Okay, so in one direction, Eckhoff showed in 1973 that there is a family of convex sets in the plane with a T3 property that is not L2. So not only does the T3 property not imply that you're L1, but it also does not necessarily imply that you're L2. So if it does imply that the family is Ln for some n, that n has to at least be 3. And here's this example by Eckhoff. Yeah, I just wanted to show you what it looked like. All right, so okay, so actually, as we pointed out earlier, the T3 property does not imply that you're L1, and actually there's no k for which the TK property implies that you're L1. So yeah, Mark.
We have a question in the chat.
Oh, sorry, I didn't see it.
Yeah. Do we always talk about TK in R to the K minus 1? So right now we've been talking about T3 and R2.
Oh, yes. So everything here is going to be in R2. So even TK property, we're talking about sets in R2. Yeah, there are generalizations to higher dimensions, but the generalizations are for hyperplanes in your dimension, not lines. So yeah. Okay. So wait, is there another? Okay, yeah. So yeah, so for every k, there's an example of a family that has a TK property but does not have a line transversal. And in 1969, Eckhoff was actually able to show that if you have the T4 property, then you are L2. So there are 2 lines for which every set in your family will hit one of those lines. And since if you have for example, if you have the T5 property, so every 5 sets can be hit by a line, that means that you have the T4 property. So So this result by Eckhoff, and so on. Like if you have the T6 property, you have the T4 property, so on. So this result by Eckhoff answers the question, what is the smallest n such that the TK property implies that you're Ln when k is greater than or equal to 4. This n is 2. So the question remains for T3. You have the T3 property. At this point in 1969, it wasn't even known if there did exist some n for which the T3 property implies that the family is Ln. And it was found in 1975 by Kramer that if a family of sets have the T3 property, then it is L5. So there exists 5 lines in the plane that hit all the sets in your family. Okay, but still, finding this smallest n was not known because it's something, at this point, it's something between 3 and 5. And then Eckhoff in 1993 showed that the T3 property implies they're L4. So at this point, the question is, okay, does the T3 property imply that you're L3, or is there an example that shows otherwise? Okay. And this is a question that myself and my advisor, Shira Zerbib, was able to answer. So we showed that a family convex sets in the plane with the T3 property implies that the family is L3. All right. And I want to go a little bit over how the proof went for this. Okay. So the proof is going to use this theorem called the Kkm theorem. If you haven't heard of this theorem, it's also equivalent to the Brouwer fixed point theorem and also Sperner's lemma. If you heard of those are a little bit more well known, I think. So let me just go into some of the basics so I can talk about the Kkm theorem. So here I'll denote delta n as the standard n-dimensional simplex. So this is just going to be the convex hull of the standard basis vectors in Rn plus 1. Okay, so the faces of delta n correspond to subsets of the integers from 1 to n plus 1. So a subset j corresponds to the face, which I call here sigma j, which is just the convex hull of the standard basis vectors ei, where I come from j. In particular, the whole simplex delta n is a face of itself when this j is all of the integers from 1 to n plus 1. Okay, so here's a statement of the Kkm theorem. So we have this covering by n plus 1 sets, a1 to an plus 1, of open subsets of the simplex delta n, such that whenever you look at each face, so if you look at the face sigma j, correspond to the subset j, this is covered by the AIs that correspond to the subset j. So these are the AIs where I come from j. Then the conclusion is that the intersection of the AIs is non-empty. So for example, in this covering condition, of just a vertex of the simplex, so like just a single standard basis vector, is a face corresponding to a singleton of the integers from 1 to n plus 1. And this condition says that every vertex, so the vertex ei is contained in ai, basically. Okay, so here's an example of the Kkm theorem for the two-dimensional simplex delta 2. Here I didn't draw the two-dimensional simplex as being embedded in R3, but we can imagine it like this just as well. So okay, so like I said before, the vertex E1, for example, is a face of the simplex, And the Kkm covering condition requires that E1 is contained in A1. So that's satisfied here, so we're good. Similarly, we need the vertex E2 to be contained in A2. And then we need the face, which is the edge from E1 to E2, to be contained in the union of A1 and A2, as it is here, so we're good. And then, again, we need E3 to be contained in A3. We need the edge from E2 to E3 to be contained in the union of A2 and A3. And same for the edge from E1 to E3. And then finally, we need the whole simplex to be covered by the union of our sets. And since all of those conditions are satisfied, the conclusion of the Kkm theorem says that we have a point and the intersection of all three of them. Okay, so that's the Kkm theorem. And now I'm going to explain how we use this to prove the result that the T3 property implies that the family is L3. Okay, so the proof uses the Kkm theorem for the 5-dimensional simplex. And remember, the standard 5-dimensional simplex we think of as embedded in R6. So a point in delta 5 will have these 6 entries, or 6 components, or whatever. So these entries are all non-negative, and since it's the convex whole of the standard basis vectors, in particular these entries will sum to 1. Okay, so the first thing that we can do is so just a couple technical things. We're assuming our family consists of compact and convex sets. And it turns out you can assume that because the sets are compact, it turns out that you can assume that your family is finite. So you have a finite family of sets. So since you have a finite number of sets and they're all compact, we can scale the plane so just that they all lie inside the unit disk. So here's our unit disk, and imagine all the sets in our family are lying inside of here. Okay, so now what we do is we just specify some point on the unit circle, say 1, 0. And then let's parameterize the circle, say going counterclockwise. Say like by cosine t, sine t. We just parameterize it like that. Now what we do, we can define points on this unit disk as so. So we can plug the first entry of our point x into our parameterization. So we're moving along clockwise by some amount. And now for our second point, we can just plug in x1 plus x2 into our parameterization. So since x2 is non-negative, we're still going to be moving counterclockwise. And then we keep doing this. So our next point, we plug in x1 plus x2 plus x3, x1 plus x2 plus x3 plus x4, and so on. And since the just a small technical thing, since the entries on this point sum to 1, when we add up all 6 of the entries, we would go back to our starting point, 1, 0. Okay, but so we define these points on the disk, but we need to somehow define lines for our problem. And one way we can do this is just for every like opposite pair of points, we just connect them by a line. So for example, here, this was our first point that we specified, and we connect it to our to this like 4th point. And we connect the second point to this 5th point, and the 3rd point to the 6th point. So basically, this is describing how a point in delta 5 corresponds to 3 lines in the plane, which will be, you can think of these as like our candidate lines given a point in delta 5. Okay. So now we gave it an interpretation for all the points in delta 5, and now we need to find our sets. that we want to use for the Kkm theorem. And to do that, first I want to define these regions. So for example, the first region corresponding to this point x, which I call R1 of x here, this will be like this this wedge here that lies in between the point that we specified and the first point denoted here by x1. Yeah, and we go along similarly counterclockwise. So this next point, that's like the wedge between these two lines, is R2 of x. The wedge between these two lines is R3 of x, and then we just go along counterclockwise like this. So notice that in this example, R1 of x, R3 of x, and R5 of x share this common triangle here. But R2x, R4x, and R6x, these are pairwise disjoint. And it turns out in basically in any possible situation, either R2x, R4x, R6x are going to be pairwise disjoint, or R1x, R3x, R5x are going to be pairwise disjoint. Basically, just depending on how this triangle is situated. Yeah.
Question. What if all of the lines just meet in the middle? Do these regions include their boundary?
Oh yeah, good point. These regions, we're considering them to be the open regions.
Okay.
Yeah, thank you.
So if there is no center triangle, if we just, drew a bunch of diameters,
Yes. Yeah,
all the regions are disjoint.
Yeah, so this triangle can degenerate to a point. Yeah. Thank you. Okay. So here's how I want to define the sets AI that we're going to use in the Kkm theorem. So we have AI contains a point x in delta 5 whenever the ith region, so yeah, the ith region is corresponding to the AI. The ith region contains a set in F. So for example, here, so we have a point x and it corresponds to these three lines. And in this example, this point x would be contained in A2 because so the region R2x contains this this circle that their circle in F. And then this point x would also be in A3 because the region R3 contains a set in F, so this oval. Okay. So that's how we define our sets AI. So I won't go over all the details for why this definition works for the Kkm theorem, but just take my word for it that if we assume by contradiction that F cannot be pierced by three lines, so so our family F having the T3 property cannot be pierced by three lines, then it turns out that the conditions of the Kkm theorem hold, and we can find some x in the intersection of the AIs. And basically, let's unravel what that means. What it means is that we have some point x such that for each region, we have some set in our family contained in that region. So here, I drew a set in R2 of x, R5 of x, or sorry, R2 of x, R4 of x, and R6 of x. And these are going to be the important regions. So we're only worried about the regions that were pairwise disjoint. And we don't really care in this instance what's happening in R1, R2, or R1, R3, and R5. There could, for instance, be like a little circle inside this triangle, and that would be contained in all of those three regions. But so the reason why I'm mostly interested in these pairwise disjoint regions is because you can kind of see by inspection that there is no line that intersects or that will hit all three of these sets. And that's how we arrive at our contradiction. So yeah, we assume that our family F with a T3 property couldn't be pierced by 3 lines. And then I claim that we were able to, or that then the AI satisfied this Kkm condition and we get this conclusion. But then this provides us with 3 sets that can't be hit by a line, which is a contradiction. Okay, so that's the whole proof.
So I gonna admit I spaced out a little and I think I caught back up, but the idea is if you have something in all of the intersections, in the intersection of all the sets, then you choose the 3 sets that don't have the center triangle in them. And you've got a set in each of those regions. And your claim is that if you have a set in each of those regions, that's going to fail the T3 condition?
Yes, exactly.
Okay.
So yeah, that's the proof of that theorem. But it turns out that this is actually something, we prove something a little bit stronger. So yes, these 3 sets don't have a line that hit all 3 of them, but not all 3 sets that don't have a line transversal look like this, basically. And so I'm going to kind of go into a definition that captures what triples of set look like this. So okay. All right, so this definition might seem a little funky at first, but I'm going to show a picture later that'll make it a little bit better, hopefully. So I will define a CK to be an ordered family of K sets in R2. So we have these K sets, F1 to FK. So okay, sorry, there's a little typo here. This should say, so if you look at the convex hull of 2 consecutive sets, and you look at the convex hull of another 2 consecutive sets, then their intersection should be empty. So this shouldn't be not equal. This should be intersection is empty. Sorry about that. Yeah, whenever these 4 sets are all different. Because if like J plus 1 was the same thing as I, then of course they won't be non-empty. Okay, so basically what this definition is trying to say is that when you take the unions of the convex hulls of these consecutive sets, what you'll get is something that resembles a closed loop with no crossings. So for example, here's a C5. The dark sets are the sets in our family. So this is F1, F2, F3, F4, F5. And whenever you look at the convex hulls of 2 consecutive sets, so for example, the convex hull of 1, 2, the convex hull of 3, 4, those are disjoint. Yeah, they have an empty intersection. So this will always, so if you like follow along the sets in order, it'll give you a closed loop with no crossings, basically. And so it turns out in this proof, what you get is that if your family of F cannot be pierced by 3 lines, then this proof tells you that you must have a C3. So it turns out this, just because of how the lines are situated and where the sets are, this will always be a C3. So the statement we actually proved in this proof was that if you have a family F that cannot be pierced by 3 lines, so it's not L3, that means it has to contain a C3 somewhere. So the contrapositive is if you have a family F with this forbidden subfamily, in this case, the forbidden subfamily is a C3, then it is L3. So kind of the point that I want to make is that these problems previously were kind of thought of as, similar to Heli's theorem. Oh, if every k sets is pierced by a line, then we have some global condition. And I believe that these problems should be viewed more as if we have a family of sets with some forbidden subfamily, then it is Ln for some n or whatever, something like that. So in this case, it's if you have a forbidden C3, you can be pierced by 3 lines. Okay, so yeah, this is that statement here. The proof that I just provided gives this result. Okay, and it turns out that when k equals 4, so if you have no C4, let me just go back a little bit. Okay. So this is an example of, oh wait, no. Okay, yeah, right here. So Eckhoff proved the result that if you have the T4 property, then you're L2. It turns out that the Kkm, a similar Kkm argument as I gave before, shows that if you have a family with no C4, then you're L2. Which actually also generalizes this result of Eckhoff. So this is another reason why I think these problems should be viewed more as if you have a family that doesn't have this, or that has a forbidden subfamily, in this case, forbids a C4, then you're L something, Ln for some n. The reason why it generalizes this result of Eckhoff is because any 4 sets that is pierced by a line, it turns out that cannot be a C4. So a C4, there's never a line that intersects all the sets in a C4. And you can kind of, yeah, here's an example of that. This is a C4, because I can follow the sets, say, I go from this top left one to this bottom left one, and, just go counterclockwise like this. And this will give me like a closed loop with these 4 sets, with no crossings. And there's no line that intersects all 4 of these. Okay. All right. So here's a generalization for families that forbid a CK. So if k is greater than or equal to 4, a family of convex sets F and R2 with no CK is LK minus 2. So for example, if you don't have a C4, you're L2. If you don't have a C5, you're L3. The same formula doesn't really work for k equals 3, but yeah, for all other k's, this formula works. And it turns out this is a tight result for k equals 4 and k equals 5. And in general, for a lower bound, turns out that there exists a family F and R2 that has no CK, and it cannot be pierced by this number of lines. So ceiling of k over 2 minus 1 lines. And this number, ceiling of k over 2 minus 1 and k minus 2 coincide for k equals 4 and 5. So that's why we have a tight result there. Oh, sorry, they don't. The ceiling of k minus 2 without the minus 1 and k minus 2 coincide. So that's why we have a tight result. Okay. And so or before, as I mentioned, Eckhoff showed that if you have the T4 property, that implies you're L2. And so that means for k greater than or equal to 4, we know that the smallest n for which your Ln was 2. So it just followed from the T4 case. Now we have a whole basically a whole, we have a new problem for each k, basically. It's not just settled by the k equals 4 case. So we have this gap between the ceiling of k over 2 and k minus 2. So the problem is find the smallest number n of k such that every family of convex sets in R2 that don't contain a ck is Ln of k. So this n of k is something in between the ceiling of k over 2 and k minus 2. Okay. And yeah, that's a problem that I'm personally pretty interested in. Okay. So since we have a little bit more time, I decided that I would introduce another related problem, which is usually known as like a fractional version of the problems that I was talking about. So instead of piercing everything in our family with some number of lines, the question is, what is the most that I can pierce with just one line? So here's a question. What is the largest constant, which here I denote as alpha k, such that for any family F with the tk property, there is a line intersecting an alpha k proportion of the members of F? So yeah, like I said, we're trying to find one line intersecting a large fraction of the members of your family. So this problem was first looked at in 1980, and they showed that as k goes into infinity, this constant tends to 1, which kind of makes sense. You'd expect the constant to be much larger if every like million of your sets has a line through them versus if every 3 of your sets has a line through them in your family. Okay. So the most recent upper bound on this is this fraction k minus 2 over k minus 1 by Holmsen in 2010. And what I'm interested is looking at what these constants are for small values of k. So for example, in alpha 3, we know that it's greater than or equal to 1/3 because in a family that has the T3 property, it's L3. So there are 3 lines that hit everything in your set. So by the pigeonhole principle, one of these lines has to hit at least 1/3 of your sets. And the upper bound 1/2, this is just this result by Holmsen. And there's nothing else is known about this constant. So this is something that I'm really interested in, is improving this bound on alpha 3. And then alpha 4, similarly, if you have the tk property, or sorry, if you have the T4 property, then you're L2. So there are 2 lines that hit everything in your set. So in particular, one of these lines has to intersect at least half of them. And then again, we have this upper bound by Holmsen, 2/3. So yeah, I'm really interested in improving these bounds and for proving the bounds on alpha k for these small values of k. Another question that you could ask is a fractional version for families that contain no ck. So, for example, if you have a family of convex sets that contains no C3, then what is the largest fraction of sets that you can hit with one line? And again, we know this fraction has to be greater than or equal to 1/3, because if you have no C3, then there are L lines that hit everything. Or sorry, 3 lines that hit everything. And I believe there's an upper bound also due to Holmson of 2/5 on that problem. But yeah, I haven't thought of that one as much, but I also think it's a very interesting problem. Okay, so that's all I have to talk about for today. So thank you for listening.
And let's all thank the speaker. Okay. Do we have any questions for Daniel?
Yeah, so thank you for the nice talk.
Thank you.
So you just stated the question that this fractional problem could be also stated with the CK property. Do you
Yeah.
know if this first part, this Kachalski-Liu theorem, would also hold then?
Oh, that's a good question. Hold on. Yeah, I would assume that it does hold because one way that I kind of think about the CK property thing is that it kind of captures how like this is very like rough, but it kind of captures how like sparsely placed your sets are. So if you have no C3, they can't be placed very sparsely at all. But if your only restriction is that they have no C, like a million, they could be a lot more sparsely placed. So I believe that yes, that constant probably would go to 1 as k goes to infinity, but I don't know for sure. But that's a very good question.
Thank you.
I think I have a related question to that. So with the TK property, if you're T6, that implies you're T5.
Yeah.
But with the CK property, if you're C6, that implies you're C5.
Oh yes. No, yeah, there's no implication either way. So
Okay.
there are examples of families with no C3 that have a C. So there are examples of families that there's no C5, there's no C3, but there's a C4.
Okay.
Yeah.
Yeah,
Actually,
because
I could even give an example. Hold on.
ooh,
Yeah. So here we just take these 4 squares, but then we put like a line in between the top 2 and the bottom 2. And this will have no C5 and no C3, but it has a C4.
okay. Yeah, because I was thinking that the first result that alpha goes to 1, like the fact that it goes to 1, not obvious, but the fact that the sequence of alphas is monotonically increasing,
Oh,
that just
yes,
comes from,
that's true. Yeah, that's a good point.
but you can't do that with CKs.
Yeah.
Any other questions for Daniel? Okay, I had one more question. I wanted to let someone else jump in, but so I understand like C4 doesn't imply C4 and T4 are distinct concepts, but I don't think I can visualize how C3 and T3 are distinct. Can you draw an example of something that is one but not the other?
Yes. Um, okay. So in the C3, okay, so being C3 turns out to be equivalent to you can draw 3 lines such that every set in your C3 were in these pointed
Right.
pointed regions. It turns out
Okay.
that's equivalent. An example of 3 sets that are not T3, but are not, but are also not a C3 are these 3. You just draw them in the non-pointed regions, like these blunt regions outside of this triangle.
So it
Um,
looks like with those sets, I could draw a different triangle, which puts them in the pointed regions. Is there?
Maybe, hold on. Let me just draw them a little bit bigger.
Okay. Okay. Yeah, sure. If they're basically the entire region, which is convex.
Yes. So, for example, if I take the convex hull of these two,
Hmm.
oh, yeah.
Wait.
Well, whoops. Actually, okay. Oh yeah. The actually the definition with C3 is a little bit weird because yeah. So just think of a C3 as when you draw the pairwise convex holes, you get something like it resembles a closed loop. So
So this thing wouldn't have an interior if you drew their pairwise convex
yes,
holes, which
basically.
is okay.
Yeah. So if
Yeah.
I draw those convex holes, I probably should use a different color. Yeah, and then I draw these convex holes. They all the convex holes, pairwise convex holes, has this intersection. Whereas a C3, I wanted to have like a hole in the middle. That makes sense. But yeah, the
Okay.
definition is a little weird for C3.
Right, because your definition required them to be disjointed. You can't have
Yeah.
that with C3, but there's a slightly
Yeah.
that makes sense. Okay, thank you.
Thanks for that clarifying point.
Okay, if there are no more questions, either out loud or in chat, let's thank Daniel again.